let's discuss the n term revised 2, right? Let's start our discussion with the question number 1. So it is said that state whether the following statements are true or false on the dotted lines, right? Okay, let's start with the statement number 1, right? Statement number 1, right? The cation with the highest charge density is the H plus ion. The cation with the highest charge density is the H plus ion, right? Let's see whether it is true or false, right? So what is charge density first of all? Charge density. So charge density is actually the charge over size. Charge over size. So one can say charge over radius or charge over size, right? Simply we denote it as the Q over R value. The Q over R value. Charge over size or charge over the radius, right? That is the charge density, right? Charge density, right? So the question is the cation with the highest charge density, right? When it comes to H plus ion, right? It is not with any kind of electrons. H plus means just a proton. H plus means just a proton, right? No electronic shells. No electronic shells. So at your size is, so the size is equal to the size of the nucleus. Size of nucleus. So and then H plus, the hydrogen is with the smallest nucleus. And another thing, hydrogen is with the smallest nucleus, right? Smallest. So size is equal to the smallest nucleus, right? So that is normally, right, in the 10 to the power minus 15 meters, right? That range, right? That range, right? So the size is the smallest, right, with the H plus ion, so that the charge density is the greatest. So H plus is with the greatest charge density, right? H plus is the particle with the greatest charge density, the ion with the greatest charge density, right? So we can say H plus is the ion with the greatest charge density. So your statement is true. So the statement is true, right? You can take the statement as a true statement, right? So that is the review for the statement number 1, right? Let's discuss the statement number 2. See what it says. When the charge density of an anion is high, polarizability of that anion is always high. Polarizability of that anion is always high. That is what it says. Let's see whether it is true or false, right? So again, what I can say is the charge density is actually equal to the Q over R value. This is the charge density, right? Okay, Q over R value, right? So we are referring to anions. So when the charge density of an anion is high, polarizability of that anion is always high. That is what it says, right? So for an anion to, right, has a greater charge density, for an anion to has a greater charge density, what should happen? It's to have a greater charge density, its Q value, the charge should be high and the radius should be small. If you are with an anion with a greater charge and a smaller radius, So such an anion is with a greater charge density, right? That is the idea, right? So one can say to have a right greater greater charge density, right? Anion should have anions should have greater charge in smaller size, greater charge and smaller size, right? This is the charge, this is size, right? Size of the radius, right? So if you think of the polarizing power, sorry, polarizability. So polarizability of an anion, when it comes to polarizability, when it comes to polarizability of anions, right? Polarizability increases. So one can say to have a great polarizability, right? Anions should have great charge but greater radius as well. The Q minus and the R minus should be large value to have a greater polarizability, right? So that is the idea. So you can say, see, the size is a problem here. Size is a problem here, right? So smaller the size, right? It is good for the charge density, but greater the size, it is good for the polarizability, right? So when the charge density of an anion is high, polarizability of that anion is always high. That statement is false then, right? You can have an anion with greater charge density with some smaller radius, then its polarizability is going to be a smaller value as the radius is small, right? As the radius is small. So you can't say that the polarizability of that anion is always that always statement is appears no. So that is a false situation, right? The statement is false. Statement is false. If you need a example here, if you need an example for this thing, right? If you need the example, right? If you need an example, compare two anions, compare two anions, compare the F minus and the Cl minus, two anions. So when it comes to charge density, because charge density as F minus is with a smaller radius, F minus is with a greater charge density than the Cl minus charge density. But the polarizability, because polarizability as F minus is smaller and the Cl minus is larger, the Cl minus is with a greater polarizability, right? So you see, even though the charge density of F minus is high, its polarizability is low, right? So you clearly see the statement is false, right? That is a review for the statement number 2, right? Let's discuss about the statement 3. See what it says. Third ionization energy of magnesium is greater than the fourth ionization energy of silicon, right? We have to compare the third ionization energy of magnesium and fourth, no? And the fourth ionization energy of silicon. Fourth ionization energy of silicon. That is our consideration here. The third ionization of magnesium is greater than the fourth ionization energy of silicon. Right? So third ionization energy of magnesium means, right? Third ionization of energy of magnesium means it is actually the, right, releasement of third electron from magnesium atom. So one can say it is the releasement of an electron from magnesium 2 plus ion, right? So that means electron is removed by magnesium 2 plus ion, right? So let's discuss about the fourth ionization of silicon as well. Because fourth ionization of silicon, it is actually releasement of fourth electron from silicon atom. In other words, we can say that means the electron is removed by silicon 3 plus ion. The fourth electron is actually removed by the silicon 3 plus ion. The electron is removed by silicon 3 plus ion, right? That is the idea. No? So the ionization energy of the magnesium is this thing, right? Magnesium 2 plus releasing the electron to come up with the magnesium 3 plus. Here it is silicon 3 plus, right? Releasing electron to come up with the silicon 4 plus. Right? The thing here is, if you are to think of the electronic configuration of this thing, magnesium is a 12th atom, the magnesium 2 plus is actually with only 10 electrons, as 2 electrons are removed. So this thing is with this configuration, 10 electronic configuration, right? It will be with 10 electrons. Because this one, silicon is a 14th atom, removing 3 electrons means it is with 11 electrons. So the configuration is this. So you clearly see, right? Removing electron from a Nobel configuration is actually very hard. It's a Nobel configuration, Nobel gas configuration. So removing electron is very hard. Electron needs great energy, right? So this is not with such a stable configuration, and by removing this electron, still you can achieve the Nobel gas configuration so that it will be easily released. Removing this electron will achieve the Nobel configuration. So it is relatively easier to remove the fourth electron from silicon. So you see, less energy is needed. Less energy is needed, so that it is very clear you need greater energy to release the electron from the magnesium 2 plus compared to silicon 3 plus. So the third ionization of magnesium is actually greater than that of silicon. So the ionization of magnesium is actually greater than that of silicon, fourth of silicon, right? So the statement is actually true. Statement is true, right? No, idea is clear, no? Right? That is a review for the statement number 3. Let's discuss the statement number 4. Thermal decomposition temperature of magnesium carbonate is greater than that of aluminium carbonate. The thermal decomposition temperature of magnesium carbonate is greater than that of aluminium carbonate. Let's see if this is true or false. Right, this is about the thermal decomposition temperatures. What is the theoretical background there? So basically, the thermal decomposition, what happens? So if you take the thermal decomposition of some metal carbonate, let's think of such metal carbonate, right? Its thermal decomposition will ultimately produce the metal oxide, right? That's solid, plus the CO2 gas, right? So metal carbonates decomposes when heating to produce the metal oxides and carbon dioxide. This is how the metal carbonates will decompose when it comes to moderately active metals, right? This is true for moderately active metals. Right? So actually what this says, if you think of, if you are trying to picturize this scenario, it is like this, no? So you have a, right, metal cation, let's say the charge is in, this is your carbonate, right? So I'll write it here, right? This is your carbonate appearing as a resonance hybrid, right? It's a carbonate. So when the heat is provided, what happens? You produce the metal oxide and the CO2, right? That means the provided heat is applied here, absorbed by this point, and this bond has broken by giving all the electrons towards oxygen to produce the O2 minus, right? That is how the situation happens now. So actually this process becomes more easy if the polarizing power of this thing, if the polarizing power of this cation is high, if the polarizing power, the Q plus over R plus value of this thing is high, if the polarizing power of that thing is high, right, then these electrons greatly attracted towards the metal, and finally these two electrons will be easily coming towards the oxygen to produce the O2 minus, right? So that when the polarizing power of the cation is high, the heat needed to break this bond is low. Heat needed to break this bond is low. So the thermal decomposition temperatures decrease when the polarizing power of the cation is high. Right? As electrons are attracted heavily towards the cation, it is easy to break this bond by forming O2 minus. Right? So that is the idea. When processing power of the cation is high, heat needed is low. So thermal decomposition temperatures decrease when processing power of your cation is high. So now we need to compare the magnesium and the aluminium here, right? So as polarizing power, of magnesium 2 plus is smaller than that of aluminum 3 plus. But this guy is with a smaller, larger radius and a smaller charge, right? So polarizing power is low here. The idea is clear, no? Mg2 plus looks like this, no? It comes aluminum 3 plus, right? And you know the things about polarizing power, right? Polarizing power, right, depends on the Q plus or R plus, right? So for magnesium, the Q plus is also high, the charge is also low. That means polarizing power is low, right? So as the polarizing power of magnesium is low, lower than the aluminum 3 plus, heat needed is high. This is kind of a inverse relationship, right? So thermal temperature is going to be high with the magnesium carbonate compared to that of aluminum carbonate, right? So that is the idea. So that depends on the porosity power of the cation, right? Greater the porosity power of the cation, lesser the heat needed. So greater the porosity power of the cation of aluminium, it is with some less heat needed for the decomposition of the carbonate, right? So let's go to the statement again. Thermal equilibrium temperature of magnesium carbonate is greater than that of aluminum carbonate. Yes, magnesium carbonate is a greater thermal equilibrium temperature than compared to the aluminum carbonate, right? The statement is true. The statement is true. So we can say the statement is true, right? So that is the review for the statement number 4, right? Let's discuss the statement number 5, right? Bohr atomic model is a nuclear model. Bohr atomic model is a nuclear model. So this is regarding atomic models, right? Atomic models. So what are atomic models in our syllabus? So you have started with the Daltons. What is the model? Golf Bohr model, right? So then we had come across Thomson's model, the palm-pudding model, right? Like plums, the electrons were here and there, which are embedded to your positively charged sphere, which are embedded to this positively charged sphere, right? So electrons are embedded to positive rigid sphere, right? This is Thomson's model. Plum pudding model. Then next came the Rutherford's model, which is the first nuclear model, right? So came up with a nucleus, right? Electrons are here and there, right? So into the nucleus, so this is Rutherford's nuclear model, right? Then comes the Bose model, right? Then comes the Bose models. So actually electrons are introduced by this model, right? The Rutherford's model introduced the nucleus, right? Then the Bose model, it has introduced the energy level concept, energy level concept, and the orbital, sorry, orbit concept, not the orbitals, but orbits concept, right? So this is about electrons travel in orbits, and actually which are with energy levels, which are actually occupying energy levels. Those two concepts are introduced by Bose model, Bose planetary model. Right, Bose planetary model, right? So nucleus is still there, right? Nucleus is still there. You have the nucleus there, right? After the Rutherford's model, with each and every model, you have the nucleus. Right? So with the Bose model, planetary model, also you are with the nucleus. So the statement says Bose atomic model is a nuclear model. Yes, it is with the nucleus, right? So Bose atomic model is a nuclear model, right? We can say Bose atomic model is a nuclear model. Nuclear model. So a statement is true. So a statement is true, right? So that is about the statement number 5. This is a review for the statement number 5. It is. Let's discuss the statement 6. Distance between two adjacent spectral series of hydrogen spectrum decreases when going towards decreasing frequency. Let's see what it says. That normally, if you think of the hydrogen spectrum, hydrogen emission spectrum, right? It looks like this, no? Right? If you are to consider the energy increasing direction here, right? So how the spectrum appears? So at the greatest, right, frequency region or greatest energy region, you are with Lyman series, Lyman series, right? Which is at the UV region, right? Then you have the Balmer series. Then you are with the Balmer series. How to write the Balmer series? Basically, take the second line onwards and copy paste here. So you'll copy the Balmer series. Balmer series of lines where you can clearly see them as those colors lines are appearing as colors, right? So second line onwards, right? Okay, this distance, then this one, then a smaller distance, right? So see, these are lines that of your Balmer series, which is actually appearing. The first four lines of the Balmer series appears at the visible region, but the others are at the UV region, right? UV and visible regions, right? The first four are at the UV region, right? The H alpha red, right? Then you have the H beta green. Then you have the blue line, right? Finally, you have it some purple line as well, right? The first four lines appear at the visible region, but the next lines will appear at the UV region, right? So then you are with the partition. How to write the partition? So take the third line onwards from here, third, fourth, fifth, and write it here, right? So this is the partition. When the electrons come into n equals 3, right? This is n equals 1 transition, n equals 2 transition, n equals 3 transitions, right? So the partition is appearing in the IR region, right? What about the bracket and fund? What about the bracket and fund? So we see the bracket and fund series of lines get overlapped with each other. Right? This is the bracket and fund. Right, which are also appearing in the IR region, right? So with this, we clearly see, right, going towards lower energy regions, the distance between spectral lines, the distance between spectral lines, see, distance between spectral lines, distance between series of lines, distance between spectral series, what we can say, distance between spectral series, like this, actually, will decrease, will decrease. Distance between spectral series decrease, right? So ultimately, bracket and fund get overlapped. Bracket and fund get overlapped, right? So that is the idea. So see, so we can say when going towards lower energy regions, you can say then going towards lower energy region. That means increase in lambda, increasing wavelength. So lower energy means wavelength is high. E is equal to HCO lambda, as these two are constants, right? E is proportional to 1 O lambda, right? Smaller the energy, greater will be the lambda. So when going towards the increase in lambda regions, right, series of spectral lines become closer to each other, right? Distance between two adjacent spectral series decrease. But when going towards lower energy region, right, that means increasing lambda, increasing wavelength, distance between two adjacent spectral lines decrease, right? So that the statement is true. Your statement is true. So that your test statement is true, right? Now, that is a review for the statement number 6. Let's discuss the statement number 7, right? Shielding effect of carbon is shielding effect of carbon is higher than that of nitrogen. Shielding effect of carbon is higher than that of nitrogen. That is what it says, right? So let's compare the shielding effects of carbon and nitrogen, right? Shielding effect, right? What is the shielding first of all, right? Shielding means this, right? So if you think of an atom, so with z number of protons, right? With z number of protons, right? At the nucleus, right? Z number of protons. So that means nuclear charge is Z, the actual nuclear charge is Z, right? If you think of electrons like this, if you think of electron appearing here, actually this electron won't feel the actual nuclear charge appearing here. This electron won't feel the actual nuclear charge appearing here. Why is that? Because of the inner electrons, as well as the outer electrons, right? Some of the nuclear charge appearing here will be screened towards this electron, right? How that is done? It is like this, right? So basically, so see, so this is the way we can say this is a nuclear attraction or nuclear charge filled by the thing, right? But what will happen, right? As these guys will repel this electron from your nucleus. See, these guys, the inner electrons, will repel your considering electrons from your nucleus. Not only that, right? These orbital electrons also repel your considering electron out from the nucleus. So that the actual nuclear charge filled by this electron is lesser than the nuclear charge filled by this electron is lesser than the actual nuclear charge available in your nucleus. So because of these repulsions of the inner and the on shell electrons, right, the nuclear charge filled by this electron is lesser than the actual nuclear charge appearing at the nucleus, right? That effect, that screening effect, this repulsion effect is referred to as the screening effect, right? Okay, this is actually the repulsion of considering repulsions of considering electron, which is done by inertial electrons and on shell electrons, right? These two kinds are referred to as co-electrons. These are referred to as co-electrons, right? This process is actually referred to as shielding, shielding or screening effect, right? Shielding or screening effect, right? That is the concept of screening or shielding effect, right? Actually, that is what these inertial electrons and the on-shell electrons do, right? To screen the nucleus from your considering electron, right? So that is the screening effect, and let's discuss how this matter with the carbon and nitrogen, right? So the screening thing is done by screening thing is done by inertial electrons and as well as onshell electrons, right? Screening is done by inertial electrons as well as onshell electrons, right? So if you think of carbon and nitrogen, the carbon, right, the thing looks like this, no? Carbon is your sixth atom. You have two electrons at the n equals 1, right? If your considering electron is this, at the n equals 2, you have, right, three other electrons, as the carbon is carrying 4 electron configuration, right? So shielding is done by these two electrons as well as these, right? So shielding is done by actually 5 electrons. So for the carbon, shielding is done by, right, these two as well as these 3, 5 electrons, 2 of inertial electrons and 3 of onshell electrons. But when it comes to nitrogen, as its configuration is, it's a 7th atom, 2 5, right? The situation with nitrogen is like this, right? 2 electrons are at the n equals 1 and n equals 2. If this is the considering electron, you are with another 4 electrons, no? Another 4 electrons as onshell electrons, right? So you can clearly see shielding is done by 6 electrons. Actually, shielding is done by inertial as well as onshell electrons, right? So you can say the shielding effect of nitrogen is greater than that of carbon. Shielding effect of nitrogen is done by 6 electrons, but here only with 5 electrons, so that shielding effect of nitrogen is greater than that of carbons, right? So that is the idea. Shielding of nitrogen is greater than that of carbons, right? So statement says shielding of carbon is higher than that of nitrogen. That statement is false then. So the statement is false. Statement is false. Shielding effect of nitrogen is greater than that of carbon. That is the correct idea, right? That is a review for the question number 7. This is review for the question number 7, right? Let's discuss the question number 8. Bond angle around nitrogen in NH3 is greater than that of NH3, right? Let's discuss about that thing, right? So this is about bond angles. Of NF3 and NH3, right? So both are carrying the same shape. Both are carrying the same shape, right? This is regarding the bond angles of species with same shape, no? Just consider NF3. This is the NH3. So the two values are very close to 107, 109 minus 2 per lone pair, right? Close to 107, right? But one is with some bit of a greater angle and one is with a slightly smaller angle. Let's discuss which one is with a slightly greater or slightly smaller angle, right? So for this thing, what matters? What matters is actually the electronegativity, right? We can consider electronegativity like this: electronegativities of atoms basically varies, like hydrogen is with the smallest electronegativity, then nitrogen, and then you are with the fluorine with the greatest electronegativity out of these 3, right? So what will happen? So as fluorine is with a greater affinity than the nitrogen, the two electrons are more closer to the fluorine like this. The two electrons are attracted towards the fluorine as fluorine is with a greater affinity. The bond is polar, so that those electrons reside more closer to fluorine. But when considering the NH3, right, as the nitrogen is with a greater affinity than the hydrogen, right, the two electrons of these NH bonds are appearing more closer to nitrogen, like this. Yes, nitrogen is with a greater affinity than hydrogen, right? So that what will happen, right? So that we can clearly see, right, bonding electron pairs in, right, NH3 is more closer to each other compared to bonding electrons in NF3. You clearly see the situation, right? So we can say the bond pair repulsions. The bond pair repulsions are heavier here as the electrons are more closer to each other. Similar sign charges will repel from each other, right? So bond pair repulsions are heavier with the NH3 compared to that of NF3 situation. As these are with some distance between them, the repulsions are less, right? So we can say bond pair, bonding electronic pair, bonding electron pair repulsions. Because those, right, those are heavy in NH3 than the NH3, right? So the bond angle is going to be high with the NH3 compared to NH3. So this will move further away from each other, making it a great angle here, right? So that we can say the bond angle of NH3 is greater than that of NH3. Okay. Again, go to the statement to check whether this statement is true or false. Bond angle of around nitrogen in NF3 is greater than that of NH3. That is what it says. No, NH3 is with a greater angle, right? So the statement is false. So the statement is false. Okay. So that is the review for the question number 8 or the statement number 8. Let's discuss the statement number 9. Right? See what it says. Boiling point of HF is greater than that of HCl. Boiling point of HF is greater than that of HCl. Right? So we are regarding two boiling points of covalent compounds. Boiling points of covalent compounds. So HF and HCl both are covalent stuff, right? Both are covalent stuff, right? So we need to apply the rules related to boiling point of covalent compounds, right? So there are two factors affecting the boiling points of covalent compounds, right? What are the two factors, right? Number one is the molecular weight, right? If delta MW, if the molecular weight difference is actually greater than 50 units, and we say the one with the greater molecular weight is with the greater boiling point. So molecular weight increases, boiling point increases, right? That is due to limited ability of thermal motions, right? When you are heavy, it is very you are very hard to move, right? When you are heavy, the stuff is very hard to move, right? So that thermal motions are not happening that much. That means it is hard to, right, liquidize a substance as well as melt a substance, right? Melt a substance as well as vaporize a substance, right? Boil a substance, right? So to convert the solid to a liquid or liquid to a gas, you need to increase the thermal motions. That can be cannot be done easily if your weight is high, if you are with some greater weight, right? That is the idea here, right? So if the molecular weight is the difference of molecular weight is greater than 50 units, definitely the one with the greater molecular weight come up with the greater boiling point. But in this case, that is not the case to consider, because HCl and HF are not with such a greater molecular weight difference, right? So we have to consider the second method, right, to discuss about the compare the boiling points of these two guys, right? So what is the second point, second part 3? That happens when molecular weight difference is less than 50 units. Under that category, the HCl and HF comes in, right? So there, what matters is the second interaction strength. When secondary interaction strength is high, your boiling points will be high, right? So for that, you need to know the increasing order of second interaction strength, right? So increasing order of secondary interaction strength varies like this. So ion dipole interactions are with the greatest among the second interactions, the strength, right? So then the hydrogen bonds, then the dipole interactions other than hydrogen bonds, finally the London forces, right? So if you compare the species here, the HF and the HCl, right? If you think of HF, because we HF as second interactions, hydrogen bonds are appear in the H bonds. H bonds and London forces are there as second interactions, because HF is some particle like this, no? Right? Among molecules, you can create hydrogen bonds, right? So it's like this, no? If you need to know stuff clearly, right? Among particles like this, HF molecules, you can think of forming hydrogen bonds, no? See, hydrogen bonds appear among HF molecules, right? Hydrogen bonds. But when it comes to HCl, so HCl is this kind of molecule. So this is negative delta, this is positive delta polar molecule. So HCl molecules are attached. Yeah, right. Dipole interactions. Yeah, dipole interactions. Right. So you know the Cl can't act as a lone pair donor. Cl can't act as a lone pair donor, right? Cl can't act as a lone pair donor. So this is just a dipole interaction. Just a dipole interaction. But here it's a H bond, right? As lone pair donors, only the fluorine, oxygen, right, and nitrogens are available, not the chlorines. As this atom, the chlorine is okay. The atom connected to the hydrogen, right? Fluorine, oxygen, and nitrogens are okay. But as lone pair donors, the chlorine is not accepted. So this is not a hydrogen bond. This is just dipole-dipole interaction. Here you have a hydrogen bond, right? So with HCl, you have dipole-dipole interactions and London forces. Among all the molecular species, London forces exist, right? So if you compare these two kind of bonds, basically hydrogen bonds are with strong interaction strength than the dipole-dipole interactions, right? So that we can say the HF molecules are with some stronger second interactions than the HCl. So HF guys are with stronger boiling points than the HCl, right? So secondary interaction strength of hydrogen bonds are greater than dipole-dipole. So that secondary interaction strength of HF is greater than HCl. So we can say when it comes to boiling points, right? HF is at a greater boiling point than the HCl, right? So what the statement says, boiling point of HF is greater than that of HCl. So the statement is true. The statement is true. That is the review for the question number 9 or the statement 9. Let's discuss the statement 10. Right? When considering an electron and a proton traveling at the same speed, de Broglie wavelength is higher with the electron. Right? See whether the statement is true or false. Right? These are regarding the de Broglie's wavelength. So what is the equation regarding de Broglie's wavelength? The lambda is equal to the Planck constant divided by the momentum. Momentum is mv, mass into volume, right? So Planck constant is always a constant value, right? 6.6 into 10 to the power minus 34 joules per second, right? That value, joules seconds, right? So they are saying that the two guys, the proton and the electron, are traveling with the same speed. It's a constant. Velocity is a constant according to this question, as both travel with the same speed. Right? So we can simplify this statement, this equation, as lambda is proportional to 1 over m, right? As these two are constants. So the one with, they are looking for the higher dipole wavelength. So the one with smaller mass is with the greater wavelength. The one with smaller mass is with the greater wavelength. So let's write. So it goes to mass, right? Electron is with a smaller mass than the proton. So the de Broglie's wavelength is then going to be a higher value for the one with smaller mass. So inverse relationship, right? Smaller the mass is, greater the de Broglie wavelength, right? So the electron is coming up with a greater de Broglie wavelength compared to the proton, right? See the statement again. When considering an electron and proton traveling at the same speed, the de Broglie wavelength is higher with the electron, So the statement is true. Right? No? So that is the review for the statement 10 in your revised paper 2, right? Let's discuss the statement 11, right? If the shape around the atom A of AB3 molecule is tetrahedral, AB3 is a non-polar molecule, right? Let's discuss whether the statement is true or false, right? So we are regarding to the molecule AB3, right? So if the shape around the atom A of AB3 molecule is tetrahedral, the shape is tetrahedral. AB3 is it tetrahedral. If the shape around the atom A of AB3 molecule is tetrahedral, so you can't have a tetrahedral geometry with only three connected atoms, no lamai. Right? For a shape to be tetrahedral, at least there should be four connected atoms. At least there should be four connected atoms. That means you can't have AB3 coming from a tetrahedral shape. AB3 with a tetrahedral shape, right? So it should be AB4. It should be AB4 if it occur with a tetrahedral shape. So the statement says it is a tetrahedral AB3, right? From that point, actually, right, the statement is false. If the shape around the atom A of AB3 molecule is tetrahedral, no, it can't be. The shape around the atom of AB3 could be trigonal plane, right? It could be T shape, right? But not the tetrahedral, right? With three connected groups, you can't have a tetrahedral shape. It could be the trigonal plane, or it could be the T shape coming from the trigonal bipyramidal electron pair geometry, right? So the statement is false. The statement is false, right? If you need a review, you can write to appear with a tetrahedral shape, right? At least, at least no, actually, you should have four connected groups. Shape, you should have four connected groups to central atom, right? That's the first point. Then you can say with only three connected groups, right? Trigonal plane and T-shaped molecules can be formed, right? You can't have tetrahedral with only three groups attached to the central atom, right? So that is the review for the statement number 11. Let's discuss the statement number 12, right? In a mixture containing acetone and chloroform, hydrogen bonds are present. In a mixture containing acetone and chloroform, hydrogen bonds are present. That is statement. Let's discuss whether the statement is true or false. Right? It's regarding hydrogen bonds. Right? So first, let's discuss about the requirement to fulfill by two molecules to show some hydrogen bond in between them. Right? This is the requirement you should fulfill to come up with hydrogen bonds. Right? So if you are to consider these two are the two molecules which are going to form hydrogen bonds, right? So one molecule should have a hydrogen actually which is connected to a highly alternative atom, which is connected to a highly alternative atom, right? So that alternative atom could be fluorine, oxygen, chlorine, or nitrogen, or other some other atoms are also possible if they are with some great affinities, right? So from the other side of from the other molecule, there should be a highly alternative atom with a lone pair, with a lone pair, with a lone pair. This lone pair is very needed, right? So as this highly alternative atom, we can consider fluorine, oxygen, and nitrogen. Not the chlorine, no? Not the chlorine. Chlorine can't come up as the lone pair donor of the hydrogen bonds, right? So what will happen then, right? As these electrons are heavily attracted towards this alternative atom, this comes with a greater positive charge and negative charge here. And as always, the electron pair of this bond will be attracted heavily towards this greater alternative atom. This will come up with a greater negative nature, so that here kind of a attraction is possible. So that is referred to as the hydrogen bond, right? This is a requirement to fulfill by two molecules to form hydrogen bonds between them, right? Okay. You can't have chlorine at this side, right? Okay. If the chlorine was there, the bond distance of the hydrogen and this thing will be larger, so that its bond strength will be lower and it is not coming under the range of hydrogen bonds, right? There's a range of hydrogen bonds now, right? Right? So it is not met, right? It is not met with the bond forming with the chlorine, right? As the distance is greater there, right? So this is referred to as the Fonkel rule then, Fonkel rule, right? Fonkel rule. So fluorine, oxygen, and nitrogen, right, can come up with both sides, but the chlorine can be used as only at this side, right? Okay, this is Fonkel rule, right? Let's discuss about the chloroform and acetone here, right? If you have to think of the acetone, it would appear like this. This is the acetone. This is the acetone. Then chloroform. Chloroform is this molecule. CHCl3. Right? You have lone pair here. So what happens here is actually, even though chlorine is not a highly alternative atom, even though the carbon is not a highly alternative atom, as that carbon is attracted to three of chlorines, which are considered as highly alternative, the electrons will be greatly attracted towards these chlorines, and the electron deficiency of this carbon is very high. Electron deficiency of this carbon is very high. That means its electronegativity is very high. When compared to this, when considering this carbon, its electronegativity is almost close to the electronegativity of nitrogen, right? Because of this effect of these three chlorines. As three chlorines are very highly electronegative, those will attract heavily the electrons of the carbon, making this carbon a highly deficient stuff, right? So that the carbon tends to attract electrons heavily from this hydrogen, creating a very, very positive charge here, right? So with the chloroform, this carbon act as a high electronegative atom because of this effect, right? This other thing is actually the only example available with this other thing is the chloroform in our syllabus, right? So the carbon here acting as a very highly electronegative atom because of this effect, and so that this hydrogen is becoming very polar or positive delta is very high with this hydrogen, so that as the electrons are turning from here is giving this guy a very strong negative delta. So you can see a formation of hydrogen bonds, hydrogen bonding between the chloroform and acetone, right? This is a chloroform, and between the chloroform and acetone, you clearly see the presence of hydrogen bonds, right? Again, let's go to the statement. In a mixture containing acetone and chloroform, hydrogen bond present. Yes, the statement is true. The statement is true, right? That is a review for the statement number 12, right? Let's discuss the question number 13. Strength of ion dipole interactions are stronger in NaCl solution than in a KCl solution, right? This is regarding the strength of ion dipole interactions, right? So actually strength of ion dipole interactions depends on the charge density of ions, right? Strength of ion dipole interactions increases when charge density. When charge density of your ion increases. When charge density of your ion increases. Right? That is the theory, right? Okay, so let's discuss about the NaCl and KCl aqueous, right? If you think of NaCl aqueous, what are the ion dipole interactions appearing there? Right? So I'll write like this. So NaCl. So this is your Na plus ion. This is your Cl minus ion. These are the water molecules, right? These are ion dipole interactions, right? Between Na plus and the water. You will see the same kind of ion dipole interactions with the Cl minus and the water as well, right? When it comes to KCl, I just consider the K plus and the Cl minus here because the Cl K plus and the Na plus here because Cl minus is the same, right? The size of the potassium ion is large. It's a KCl situation, no? Size of potassium ion is bit larger, right? Compared to the size of the sodium plus ion, right? It's a smaller size, right? Okay, so the ion dipole interactions between the K plus and water can be represented like this, right? No? Anyway, right? We know no need to compare what this thing because that is common with the both the guys, right? So when considering these two guys, right, the charge density is greater with the sodium plus compared to K plus, right? So charge density of sodium plus is greater than that of K plus because of the radius. Both are carrying the same plus one charge, but when it comes to radius, sodium ion is with a small radius. That means charge density is high. When the charge density is high, the strength of ion dipole interactions becomes larger. So ion dipole strength, when it comes to ion dipole strength, right? The NaCl is with a greater ion dipole interaction strength than the KCl. So one can see Na plus Aq is with a greater ion dipole strength than the K plus Aq. So we can say the ion dipole interaction strength in NaCl is greater than that of KCl. So in NaCl, aqueous is greater than that of KCl aqueous. Right now? See what they are saying? Strength of ion dipole interactions are stronger in NaCl solution than in a KCl solution. Yes, that is true. The statement is true. The thing is, ion dipole interaction strength depends on the charge density of the ion. Now here, what will attract to the positive ions via its negative delta terminal, right? It's clear, no? You know the stuff, no? Remember, මතක නේද? හරි? What will attract using its negative delta terminal, right? Towards the cations. That is the ion dipole interaction strength, right? Those are the ion dipole interactions, right? Towards the negative ions, what will attract from its positive terminal? The hydrogens, right? That is understood, no? Right. So this is the review for the statement 13, right? Let's discuss about the statement 14. See, all the electrons in an atom are identical. All the electrons in an atom are identical. Right? That is kind of a controversial statement, right? So what we can say is all electrons in an atom are identical with charge and mass. Charge and mass. That is why all of them giving you the same EOM ratio. That is why all of the electrons in your atoms are giving you the same EOM ratio, right? But differs with their energy. But differs with their energies. So you know the 1s electrons are with lower energies than the 2s electrons. 2s electrons are with lower energy than the right 2p electrons. Like that, no? So electrons are not identical with energies. Electrons are identical with charge and mass. All the electrons in any atom or the same atom are identical with charge and mass, not with the energies. Right? The statement says all the electrons in an atom are identical. You have to take it as a false statement. If they are saying all the electrons in an atom are identical with mass and charge, then the statement is true. But if they are just saying all the electrons in an atom are identical, that is false. They will differ with their energies, right? So we have to take the statement as false, right? As electrons differ with their energies, we have to take the statement or take statement 13 for the statement 14 as false. But the other if the statement was all the electrons in an atom are identical with mass and charge, the statement is true. But just saying identical is giving you a wrong idea, right? So as those are different with the energies, right? Okay. So for the statement number 14, we have to take the statement as a false statement. Let's discuss about the statement number 15. See what they are saying. Deflection of Na plus ions in a magnetic field is greater than that of Ca2 plus. Right? See, this is about deflection of charged particles in a electromagnetic field. So what is the theory here? The theory is all about the deviation angle, no? Deviating angle, right? Deviation angle theta is actually proportional to, right, charge over mass ratio. Deviation angle theta is proportional to charge over mass ratio. When the charge is high, you can see a greater deviation than a discharged particle. When the mass is high, the deviation is less. Right? So we can apply this theory to come up with the answer. So this is about diffusion of Na plus ions and the Ca2 plus ions. Right? So Na plus and the Ca2 plus. So Na plus is like this, only with 10 electrons. Ca2 plus, right? 10 electrons. What is the mass here? 23rd atom, right? 23rd atom. Sorry, 11th atom. That means 23 is the mass number. Calcium 2 plus. Calcium 2 plus is with 18 electrons. It is your 20th atom. The mass number is 40. Mass number is 40. So what we need is these two numbers, mass and the charge. Mass and the charge. Right? So looks like the mass is low with this one, the charge is high with this one, right? So some problem is there. Let's come up with a right calculation. So first the EOM for this ODM plus. So we can write the charge number is plus 1, the charge number is just plus 1, and the mass number is 23. Mass number is 23. Right? For the EOM ratio of calcium 2 plus, right? So it's 23 of protonic mass, right? We can say 23 of protonic mass. So yes, with the 23, you are with protons and neutrons. We can consider the protons and neutrons are with same masses, right? As those guys are with closely related masses, right? So for this one, you can write it as 2 over 40 of the protonic mass. You can simplify this thing, it will be like 1 over 20 of MP. So you clearly see the EOM ratio of this thing is smaller and this thing is high. So smaller the value at the bottom, the numerical value is high. So EOM ratio of calcium 2 plus is higher. That means the deviation angle of calcium 2 plus is going to be high, right? So we can write because deviation angle than the sodium plus, calcium 2 plus is with a greater value as its EOM ratio is high. When the EOM ratio is high, the deviation angle will be high, right? So diffraction of Na plus ions in a magnetic field is greater than that of calcium 2 plus means that is false, right? So calcium 2 plus is with a greater deviation angle than the sodium plus, right? So the statement is false. Statement is false, right? So that is a review for the statement 15. Let's discuss the question number 16. So with the 16th to 20th questions, the instructions are given like this, right? Write the answers to the questions given below on the dotted lines. That is the instructions given. Right? Let's discuss about the 16th question. Of the three elements O, F, and Na, which one has the highest third ionization energy? Right? So this is regarding the third ionization energy. Third ionization energy. So we are with O, F, and Na. The atoms are oxygen, fluorine, and neon. Right? See the third ionization energy. How we are supposed to come up with this kind of a question? First of all, write the trend, right? And the zigzag, because these guys are belongs to the same row, right? So first write the zigzag here. This is for the third ionization, right? And zigzag for the third ionization. Third. So we can say third ionization, right? So these are the points. Regarding to the longer lines, the first longer line is with only 2 points, which are at the starting point and the end point. But with the second and third longer lines, not only the corners but also the center carrying some point, right? Okay, like this now. So when it comes to third ionization, right, always the minimum value of third ionization belongs to the group 3 element. Group 3 element. So group 3 element is always with the I1 minimum, right? So I3 minimum. I3 minimum, right, with group 3 element, right? So releasing the third electron will give it a noble gas configuration. Releasing the third electron will give it a noble gas configuration. That is why the group 3 element is with the lowest third ionization, lowest third ionization, right? As you are achieving the most stable configuration, the third electron will be more keenly released with very less amount of energy by the group 3 atom, right? Okay, so we're starting with group 3. This is the second row, guys. So the group 3 of the second row is actually what? Group 3 of the second row is, right, second row beryllium, sorry, that is lithium, beryllium, boron. Boron is the group 3 guy of the second row, boron. Then you have the carbon, nitrogen, oxygen, fluorine, and neon, right? These are how the atoms arise, right? Okay, let's compare the guys here. So if you have to complete this thing, you can complete the ones, right? So beryllium appears here and the lithium appears here, right? So that is okay, no? Anyway, so what we are referring here is all about these three guys, right? Oxygen, fluorine, and neon, right? So you see the oxygen appearing here, with this point, fluorine appearing here, and neon appearing here, right? So when it comes to third ionization energy, right? The fluorine is with the greatest value. Then the neon, this least value is with the oxygen out of these three, right? So of the three elements, they are looking for the highest third ionization. So the highest third ionization appears with fluorine. Highest is with fluorine out of these three, right? So the answer is fluorine. The answer is fluorine. That is the review for the statement 16. Let's discuss the statement 17. Of the three species, CO, CO2, and carbonate, which one has the shortest carbon-oxygen bond, right? Shortest carbon-oxygen bond, right? So this is about the bond length. The question is about the bond length. Bond length, right? Actually, two factors affecting the bond length, right? What are the two factors? Right? The bond order. Number one is bond order, right? It says, right, the bond order is BO, right? It says when the bond order is high, when bond order is high, that means number of bonds between the two atoms, right, is high. That means your bond length is low, right? Triple bonds are shorter than double bonds. Double bonds are shorter than single bonds. When you are with more number of bonds between the two atoms, the bond length is more. That is the first fact, right? The second consideration is when the bond order is equal. When bond order is equal, we have to consider the S character of hybridization. No? S character of hybridization. Well, right? S character is considered, right? What it says? It says when S character is high, that means your orbitals are more closer to your nuclei, right? So when S character is high, your bond length is small. S character is high, bond length is small, right? Those are two things to consider here. Right? Let's discuss, right, how to compare these three guys here, right? So what are the three guys? Carbon monoxide, carbon dioxide, and CO. First, the carbon monoxide. So carbon monoxide comes with this kind of a Lewis structure where the bond order is equal to 3. The carbon dioxide, the only stable Lewis structure you can draw for the carbon dioxide is this. So carbon oxygen bond order is 2. Between the carbon and oxygen atoms, only 2 bonds are appearing. Here between the carbon and oxygen atoms, 3 bonds are appearing. This is the only stable Lewis structure you can draw for carbon dioxide. So that is the naturally existing form in nature. That is what we need to consider, right? When it comes to carbonate, right? It's one of the Lewis structures can be drawn like this. So it appears as a resonance hybrid, right? So you can have the double bond here as well as here. So it appears as a resonance hybrid in nature. Resonance hybrid is the base structure representing the properties of the carbonate. If you are with more than If you can draw more than one stable Lewis structure, those guys will appear as resonance hybrid in nature. Naturally, existing structure should be considered, right? So this is resonance hybrid, right? So what about the bond order here? Basically, one 5 bond is going to delocalize in 3 places. One 5 bond in 3 places. So per one place, it is just 5 over 3. 5 bond order is 5 over 3. Right? So the bond order between the carbon and oxygen, the number of bonds between the carbon and oxygen here is one complete sigma bond and 1/3 of a 5 bond. That is 1.33. 1.33. One complete sigma bond and 1/3 of a 5 bond. Right? 1/3 means 0.33, right? That is the bond order. Right? So for the carbon monoxide, is bond order is 3. Carbon dioxide is bond order is 2. For the carbonate, bond order is 1.33. So we can come up with this form to get a correct answer, right? So they are looking for the one with shortest CO bond. The one with shortest CO bond appears with the one with greatest bond order. The one with greatest bond order. So carbon monoxide is the one with greatest bond order. So this is the one with shortest bond length. Right? So the answer is carbon monoxide. That is the review for the question number 17. Let's discuss the question number 18. See, of the three compounds SO2, SO3 and SOCl2, which one has the least alternative sulfur atom? Least alternative sulfur atom, right? So this is about the electronegativity. Electronegativity. Right? So what are the considerations? So if you are considering species with same electronegativity in your Pauling scale, right? The electronegativity will vary with chemical environment too, right? We have to consider that too, right? So electronegativity of an atom varies with its chemical environment, right? What are the considerations? First, the hybridization. First, the hybridization. When S character of the hybridization is high, right? Your electricity is high. Right? The second consideration is when the hybridization is same, we have to consider the charge on the atom. When charge on atom is high, your electricity is high. Right? Third thing, when these two are equal, you have to consider the oxidation state. When positive nature of oxidation state is high, your electronegativity is high. Finally, you have to consider if all the three are the same, you have to consider the electricity of connected atoms. When electronegativity of connected atoms, when those are high, your considering atoms electronegativity is also high. Considering atom is also high. Those are the four chemical environments, which will decide the iterative variations, right? Okay, let's discuss the situation here, right? So we are with SO2, SO3, and SOCl2. First, the SO2. SO2 is this kind of a stuff. I'll just write the Lewis structure, that is enough to copy the answer. Right? This is SO2. It is with 1, 2, 3 sp2 hybridization. When it comes to SO3, SO3 is with this stuff. So it is also with sp2 hybridization. Number of sigma bonds and lone pairs equals to 3 in the sulfur. Then you have SOCl2. Right? SOCl2. Right? So 1, 2, 3, 4, 5, 6. 6 electrons should be there around sulfur, so that sulfur carrying some sp3 hybridization. sp3 hybridization. Right? So they are looking for which one has the least iterative sulfur atom, least. So when the S character is low, your iterativity is low, right? You can use this theory to decide the answer here. When the S character is low, see the sp3 hybridization, that is where the least S character appears. More p character is there, least S character. Out of 4 orbitals, only 1 is S. So here you are with the least iterative, right? When S character decreases, electronegativity decreases, right? So the answer is SOCl2. The answer is SOCl2. Right now? So that is the review for the question number 18. Right? Let's discuss the question number 19. Of the three metals, lithium, sodium, and calcium, which one has the highest melting point? Highest melting point, right? This is about melting points of metals. Melting points of metals, right? So the idea is when metallic bonding strength increases, your melting points will increase, right? When the metallic bonding strength increases, your melting points will increase, right? That is the theory we are going to use here, right? And we know there are three factors affecting the metallic bonding strength, right? What are the three factors? Number of electrons released to electron C, right? When it is high, your metallic bonding strength is high, so your melting points would be high. The second factor is size or the radius of cations, of metal cations in your electron Z, right? In your metallic bonding lattice, right? So when that radius is low, the charge density is high, so the metallic bonding strength will be high, giving you a greater melting point. The third fact is actually the ionic nature. Basically only considered in D elements. in our syllabus, right? So that says in the ionization energy, is low, you can release more electrons to electron C and your metallic bonding strength will be high. So your melting points are high, right? So that is the idea, right? So let's concern the three guys here. So lithium, sodium, and calcium. No D block guys are appearing, so we need to look for these two things, right? These block guys, right? Lithium, sodium, and calcium, right? Lithium, sodium, and calcium. First thing is this point. First thing is this point, right? First consideration is this. If we are unable to come up with this one, we consider this one. If you are still unable to come up with the answer for this thing, we go for this one, right? So number of electrons reduced to electron C, that is the first consideration. Electron C, right? So when it comes to that, right, lithium gives only one electron, and sodium that is also giving only one electron, but calcium is providing two electrons to the electron C, right? Because calcium producing calcium 2 plus ions, right? Okay, this is all the electrons when it comes to S block elements, right? They are all the valence electrons, right? So they are looking for highest melting point, highest melting point. So as the number of electrons released to electron C is high with calcium, basically calcium means with a greater metallic bonding strength, so as the melting points, right? So metallic bonding strength of calcium is greater than that of lithium and sodium, right? So melting point because the melting point, the calcium is with a greater value than the sodium and the lithium, right? So the melting point of calcium is the one with the greatest value, right? So calcium is the answer. So your answer is calcium, right now. That is for the question number 19. Let's discuss the statement 20. Of the three elements, nitrogen, magnesium, and sulfur, which element has the highest effective charge? Which element has the highest effective charge? Let's see. And this is about the effective charge, right? Effective nuclear charge. And that is actually the charge felt by an considering electron, right? Charge felt by an considering by a considering electron, right? That is what we mean by the effective charge, right? That will be given by this equation, no? Effective charge is equal to actual nuclear charge minus the shielding effect, no? Actual nuclear charge minus the shielding effect, right? That's the equation, right? Anyway, when it comes to period trends, right? Period trends as a period trends as well as the trends going down the globe, right? We should note these things as well, right? Right? It comes every charge going towards right and going down a group. We should know, right? So going towards right of a period, effective charge increases. The charge increases. That is why actually the atomic radii become smaller going towards right of a period, right? So atomic radii become smaller as the valence electrons will be greatly attracted towards the nucleus, going towards right of a period, right? So we can say effective charge increases going towards right of a period. Then going down a group, is it if EFF do not change. EFF do not change going down a group, right? Going down a group, if new charge won't change, right? This is what you should know. Going towards right of a group of a period, this is what happens. Going down a group, right? So let's apply these theories to come up with the atom with greatest affinity charge out of the nitrogen, magnesium, sulfur, right? Okay, let's take the positions of those guys at the periodic table, right? So those belongs to second row and as well as third row, right? So this is the P block: boron, carbon, nitrogen, oxygen, fluorine, neon. Magnesium is also there. No? Lithium and beryllium is also there. You have the magnesium here, right? Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, oxygen, argon. No? Those are things. No? So we have to compare the nitrogen, magnesium, sulfur. Nitrogen, magnesium, and sulfur. Those are the ones we are trying to compare here, right? Okay. So basically, you can take the nitrogen to the third row. You can take the nitrogen to the third row as nitrogen and phosphorus are with same affinity charges, right? As going down the group, affinity charge won't change, do not change. That means nitrogen and phosphorus values are same. The phosphorus is at EFF of phosphorus is actually same as nitrogens, right? With this theory, right? So nitrogen value is equal to the phosphorus value, right? So that now we can compare. Going towards right, if charge increases. Going towards right, if charge increases. So is a DFF values in considering magnesium is with the lowest value, then the phosphorus actually which is equal to the nitrogens, and then the sulfur is with the greatest unit charge according to these theories, right? So the answer is sulfur. The answer is sulfur, right? So answer is sulfur. Right? So that is the review for the 20th question. Right? With that, we are going to wind up for today's session. Right? Let's meet with the third end-term revised paper next week. Until then, goodbye.